No, we didn't. Uh, are all the posters not resized? Fine.
n minus 1 into
Hello everyone, welcome to Summer School by Mathematics Club IIT Madras. In today's session, we will be learning about numerical methods presented by me and Satvik. In this session, we will be learning what numerical methods are, why they are useful in today's world, and then we will study some of the most commonly used numerical methods in our day-to-day life. Before we begin our session, kindly mark your attendance by scanning this QR code. The Google form attached to the QR code will be open for the next 5 minutes. Okay, for those who have not filled the attendance yet, we will be keeping the form open for an additional 3 minutes. Kindly fill the form quickly. Yeah, so I hope everyone has marked their attendance. So now let's begin the session. First of all, what are numerical methods? Numerical methods are basically some computational techniques that are used to obtain the approximate solutions to some kinds of mathematical problems. These are useful whenever it is not possible to find the exact solution of a mathematical problem, or even when it is very difficult to find the exact solution. So why do we need these numerical methods? Most of the real world problems do not have an exact solution. Even if they have an exact solution, it is very difficult to find them. These numerical methods provide us some computational procedures which can be applied to find the approximate solution to these kinds of mathematical problems. Due to this reason, these are widely used in engineering, sciences, finance, and many other fields. So what kinds of numerical methods are we going to cover in this session? We will first study the Newton-Raphson method, which is used for solving equations and systems of equations. Then we will move on to the trapezoidal rule, which is used for numerical integration. After that, we will look into some techniques used to solve ordinary differential equations. We will even compare these methods in terms of their accuracy and computational labor involved. So let's start with the Newton-Raphson method. Before we move on to the working of the Newton-Raphson method, let us consider an equation, x square minus 24 equal to 0. We know that the positive solution of this equation lies between the integers 4 and 5. But what about the exact value of the solution? In this case, we might use the quadratic formula to find the solution of the equation, which is square root of 24, approximately 4.8989. But what if we have a higher degree polynomial for which we do not have any kind of formula to find the exact solution or any kind of complicated equation? In such cases, this Newton-Raphson method is very helpful in finding an approximate solution of the equation. Now let us move on to the working of the Newton-Raphson method. Suppose that we have to solve an equation f of x equal to 0. In that case, we choose an initial guess xi and draw a tangent line at that point. This tangent line is extended to meet the x-axis at a point, say, xi plus 1. The slope of this tangent is simply the derivative of the function f of x. Using the 2-point formula, we can also find the slope of this tangent. Therefore, we get f dash of xi is equal to f of xi minus 0 divided by xi minus xi plus 1. When we rearrange these terms, we get the equation xi plus 1 equals xi minus f of xi divided by f dash of xi. We will be using this formula repeatedly to reach to the exact solution of the equation f of x equal to 0. We will be using this equation until the difference xi plus 1 minus xi is sufficiently small. Then we can consider the value xi plus 1 as the solution of the equation f of x equal to 0. Now you might get a question, why did we choose the tangent line? As you all know, around a small interval at a point of the function nearly behaves like a line, and it is easier to deal with lines compared to curves. That is why we have chosen the concept of tangent line in this Newton-Raphson method. One challenge involved in this Newton-Raphson method is computation of the derivative of the function f of x. As you all know, there are a large number of functions for which it is very difficult to find the derivative. In such cases, we can use this approximate formula. F dash xi is approximately equal to f of xi minus 1 minus f of xi divided by xi minus 1 minus xi. Again, we substitute this approximate value of the derivative in the Newton-Raphson equation and we get this modified equation. Xi plus 1 equals xi minus f of xi multiplied by xi minus 1 minus xi divided by f of xi minus 1 minus f of xi. This modified Newton-Raphson method is also known as the secant method. As you can observe here, this secant method requires two initial guesses, xi minus 1 and xi. Not only this, we also have an alternate method to find the derivative of the function, which is given as follows. F dash of x equals So yeah, this is another approximate formula for finding the derivative of the function. F dash of x equals f of x plus dx minus f of x divided by dx. The idea behind this formula is that the function behaves approximately like a line at a small region around the point x. Therefore, we choose a dx which is sufficiently small, and depending on the value of the dx, the accuracy of the derivative also varies. And as you can see, if we use this approximation for the derivative, just like the original Newton-Raphson method, this modified method also requires only one initial guess. Now, Newton-Raphson method is not only limited to the equations involving single variable, This can also be used for equations which have multiple variables. But the only condition that we have to keep in mind for solving such equations is that the number of variables that we have to solve for must be equal to the number of equations that we have. But before moving on to the Newton-Raphson method for multiple variables, let us know what a partial derivative is. A partial derivative is basically the measure of the change of a function with respect to one variable, keeping all the other variables in the function constant. For simplicity, let us consider a two-variable function f of xy. Here, dou f by dou x represents the partial derivative of the function f with respect to the variable x. That is, it measures the change in the value of the function f with respect to the change in the variable x. Similarly, dou f by dou y represents the partial derivative of the function f with respect to the variable y. That is, it measures the change in the value of the function f due to the change in the variable y. These partial derivatives are very important in the construction of the Jacobian matrix, which we will use in the multivariable Newton-Raphson method. Let us consider a two-variable system of equations f of xy equal to 0 and g of xy equal to 0. The Jacobian matrix for these two equations is given by dou f by dou x, dou f by dou y, dou g by dou x, and dou g by dou y. As you can all see here, we have the partial derivatives of both the functions with respect to both the variables in the matrix. Now the Newton-Raphson formula for this two-variable system would be xi plus 1 equals xi minus Jacobian inverse multiplied by the function matrix f. Here this xi and xi plus 1 are the variable matrices. This J inverse is the inverse matrix of this Jacobian matrix, and f is the matrix of the functions that we have taken into consideration. So let us look at how these matrices are represented. This is the representation of the variable matrix X. And this is how we represent the function matrix. And depending on the number of variables, we also have to provide the same number of initial guesses. Therefore, the Newton-Raphson method can be used to solve multiple variable systems as well. But the condition that we have to keep in mind is that the number of variables must be equal to the number of equations present. Suppose we are solving for some n number of variables, then we must have n number of equations involving these variables. Now that we know how to use the Newton-Raphson equation for solving equations, let us consider an equation involving this Newton-Raphson method. Solve x square equal to 24 using the Newton-Raphson method with an initial guess x equal to 4. As you can easily observe here, the function f of x here is x square minus 24. And the derivative of this function is 2x. Now let us find x1 by using the Newton-Raphson method. x1 equals x0, which is 4, minus f of x0, which simplifies to minus 8, divided by f dash of x0, which is 8 again. This x1 simplifies to be 5. We will use this value of x1 to find x2 which will further be used to find x3 and so on. This is a table showing the subsequent values of x. As you can see, we got the value of x1 to be 5, the value of x2 is 4.9, and subsequently we had values of x3 and x4 as well. Clearly, the difference between x3 and x4 is very small. Also, the value of the function for this value of x4, that is 4.898979, is roughly equal to 0. Therefore, we can consider this value of x as the approximate solution of the equation x square minus 24 equal to 0. Remember that this is only one of the two solutions that are present for this equation. There also exists a negative root which is equal to minus 4.8989, as you all know. Now that we know how this Newton-Raphson method works, let us look at a graphical representation of this Newton-Raphson method. Let us consider the same equation that we have taken in the example, f of x equals x square minus 24, with an initial guess x equal to 4. So here this red colored curve represents the graph of the function f of x equal to x square minus 24. And since our initial guess is 4, we will be drawing a tangent at x equal to 4 to the curve x square minus 24. As you all can observe here, this tangent meets the x-axis at x equal to 5. This line x equal to 5 meets the curve of our function at the point 5 comma 1. So our value of x1 is 5. Now we will be drawing a tangent at this point 5 comma 1, which is represented by the black line in this graph. So now as you all can observe, this meets the x-axis at x equal to 4.9. Now we repeat this procedure by drawing a tangent again at x equal to 4.9. Here the green line represents the tangent to the curve at x equal to 4.9. As you all can clearly observe, this is very close to the curve of our function. This meets the x-axis at the point x equal to 4.898, which is the value of our x3. Subsequently, we will be drawing the tangent again at this x equal to 4.89898 to find the value of x4. If this accuracy is acceptable according to our problem, then we might end up at x3 itself. Now, as I have mentioned earlier, we also have a negative root for this solution. Let us change the initial guess and check if we can find the negative root as well using this Newton-Raphson method. In this case, we will be considering the initial guess x equal to minus 4. Here, as you can see, the tangent to this curve at x equal to minus 4 meets the x-axis at the point minus 5 comma 0. So this line x equal to minus 5, this line x equal to minus 5 meets our curve at the point minus 5 comma 1. Minus 5 is the value of our x1, as you can observe here. Now we will be drawing the tangent to the curve at the point minus 5 comma 1 and observe where this meets the x-axis. Just like the previous case, the black line here represents the tangent line, the red curve represents our function. So clearly this tangent line meets the x-axis at x equal to minus 4.9. And the line x equal to minus 4.9 meets our curve at the point minus 4.9 comma 0.01. Now we will again be drawing a tangent at this point minus 4.9 comma 0.01 and observe where this meets the x-axis. Clearly, as you can see here, this tangent line represented by this green line meets the x-axis at minus 4.89898, which is roughly equal to our x3 value. If we expect more accuracy, we can again draw the tangent line at x equal to minus 4.898 to the curve and check where it meets the x-axis. But depending on our accuracy, we can stop at x3 as well. Now that we have seen how this Newton-Raphson works and how this converges to the exact solution, let us see if there are any limitations to this Newton-Raphson method. Just like any other numerical method, this Newton-Raphson method also has some limitations. These are some of them. The Newton-Raphson method requires a sufficiently accurate initial guess. Depending on our initial guess, the Newton-Raphson algorithm may converge to our desired solution, or it may converge to a different solution, or it may not converge at all. Next one. We have to compute the derivative of the function at every iteration, which can be computationally laborious. Despite using the approximate methods for finding the derivative, it can be computationally laborious for a large number of functions. Not just that, for functions having more than one root, depending on our initial guess, the Newton-Raphson algorithm may converge to a different root than we expect, like we have observed in the previous case. Depending on our initial guess, whether it is positive or negative, the Newton-Raphson algorithm converged accordingly. Not just that, instead of moving closer and closer to the exact root, sometimes the value of x may move farther and farther away from the exact solution of the equation. Therefore, it is necessary to find a suitable initial guess such that it converges instead of diverging. And for equations having repeated roots, the Newton-Raphson algorithm converges very slowly. One reason behind this is that the x-axis itself is a tangent to the graph of the function at the point of exact solution. Now let us look at some of the applications of this Newton-Raphson method. Some applications of this Newton-Raphson method include optimization problems where we have to find the maxima and minima of the functions. This can also be used in the robotic kinematics to find the positions and angles of the joints. Like if you have an equation which determines the position of the robotic arm, this Newton-Raphson method can be used for solving the equation and finding the position of the arm. Not just that, this can also be used in circuit analysis to solve the system of equations that we obtain from the circuit. In short, wherever we have to solve equations or a system of equations, Newton-Raphson method is one of the commonly used methods. Any questions so far? Okay, so one of the questions that we got is regarding the formation of the Jacobian matrix in the multivariable Newton-Raphson method. The intuition behind this Jacobian matrix is similar to the one which we have observed for the single variable Newton-Raphson method. Just like we have drawn the tangent line for the single variable Newton-Raphson method, we will be considering a tangent plane if it is a two variable function, and see where it intersects the xy plane and proceed in that way. And similar and a similar way is applicable for higher dimensions as well. Okay, so if there are no more questions, we will move on to the trapezoidal rule, which is used for numerical integration. This will be taken up by Satvik.
Hello everyone, I hope my screen is visible. Yeah, numerical integration. First of all, why do we need numerical integration? Because sometimes there are functions which may not be integrable or which are very tough to integrate. Means they are integrable, but they are very computationally expensive to integrate. That's why we use this numerical integration to solve such questions. For example, uh, if we have a velocity function as a function of time, and we want to calculate the distance uh, in the time interval, let's say from 1 second to 3 seconds. So we use integration to calculate this. Basically, what integration means is area under the curve. So we use numerical methods to approximate for some non-integrable functions. So one of such method used for numerical integration is trapezoidal rule. So basically, what's the intuition behind the trapezoidal rule is uh, the area under the curve. Let's say we want to find area under this curve from A to P. This is f of A. This is f of B. So what is the basic approximation possible for a curve? It's line. So we approximate this curve with a line joining these 2 points. So if we want to calculate this area, we can approximate this area using area of this trapezium. As we know, area of trapezium is height into the average of the parallel sides. So we'll get this integral turns out to be b minus a by 2 into f of a plus f of b. So is this always a good approximation? No. this is not always a good approximation, because if the curve is like this, as you can see, if we approximate using trapezium, we'll get only this area, but the area under the curve is much more. So what we basically do is we divide the interval. We divide this interval into many subintervals, and we divide the area into many trapeziums, and sum those areas to hope to get a better approximation than using a single trapezium. So let us say this is A. Let us say this is A and this is B. Here we divide the subinterval A to B into 3 trapeziums. So yeah, for every function, we generally divide the subinterval into 10, 20, or even sometimes 100 subintervals to get more accuracy. So here H is the common, H is the length of each interval, which is represented by B minus A by N. If you want to divide it into N subintervals, and we'll add the areas of all trapezoids to get the area under the curve. So this is basically the formula for the to find the numerical integral of this integral. So h is the length of each interval, h by 2 into f of x naught plus 2 times f of x1, x2 up to xn minus 1 and xn. Xn is point B, x naught is point A, and the rest all are the in-between points. This is the most used method in practical computations. There are other methods also, but this is used if you want accurate results up to some 4 or 5 decimals. So let us see an example regarding this. So approximate ln phi using trapezoidal rule. As you know, the integral of 1 by x from A to B turns out to be ln B minus ln A. So we use the trapezoidal rule in such a way that from interval 1 to 5, which turns out to be ln phi. So we can choose as many as subintervals you want. Here I am choosing 6 subintervals. If you choose some 10 or 20 subintervals, you will get even more accurate result. So let us find out h, the length of each subinterval. 5 minus 1 by 6, because n is 6, which is equal to 2 by 3. So this is the length of each subinterval. So in A point means x naught is equal to 1, which is the starting point of the interval, and x1, first point, which turns out to be 5 by 3, because x plus x naught plus h, and x2 turns out to be 7 by 3, and x3, x4, x5 until x6. x6 is 5 itself. So we use the formula to approximate the integral. I is equal to h by 2 means 1 by 3 into f of x naught 1 by 1, which is 1, and 2 times f of x1 plus f of x2 plus up to f of x5, 3 by 5 plus 3 by 7 plus until so on. And plus 1 by 5, which is f of x6. So after calculating, this turns out to be 1.6436, and the exact value of ln 5 is 1.60943. So there is a error 0.04. But if we choose more number of subintervals, like for example, if you try with n is equal to 10 or n is equal to 20, you can try this after the session, you will get more accuracy. So What are the drawbacks of this trapezoidal rule? First of all, if the function has significant curvature, means for example, if a function is like this, so if we approximate the area with one trapezium from A to B, we'll get this much extra area, right? So that's why we choose many subintervals. But to obtain the precise result, the interval must be divided into many subintervals. But the problem with many subinterval is it takes so much computational cost that it's not preferred. That's why there are other methods such as Simpson's rule or Gaussian quadrature. Generally, we use those methods if we want more precise results with less computation. The idea behind Simpson's rule is here we are approximating the curve with straight lines, right? These curve with straight lines, right? So the idea behind Simpson's rule is we approximate the curve with parabolas instead of straight lines to hope to get more accurate results. That's why those are used if you want high precision. But if we can get away with like up to 4 decimals accuracy or 3 decimals accuracy, we can use trapezoidal rule directly. There are some questions. So, what are the applications of trapezoidal rule? Sometimes we know, for example, if we have an object, we know its velocity at particular time intervals, like at t is equal to 1, velocity is 2 meters per second. At t is equal to 2, it's 3 meters per second. At t is equal to 3, it is 5 meters per second. So if you want to compute the distance and we don't know the velocity as a function of time, so we basically use this trapezoidal rule. So we divide the interval in such a way that we can use the data points we have and try to approximate the distance traveled by the particle. So that's an application in physics. And in the same way, if we have if you want to calculate work done by the force, we can use this trapezoidal rule. And in the engineering also, if you want to calculate area and volume there are many shapes which don't have formula for area and volume. So we use this trapezoidal rule to approximate the integrals for area and volume. So it's used in engineering and it's also used in signal processing and data analysis. In statistics also, if you know about the continuous probabilities, there we use there are many integrals show up. Most of them don't have solution. So we use trapezoidal rule to approximate the area. So yeah, let us see some illustration of this trapezoidal rule. As you can see, this is the function 1 by x. And if you want to find ln 5, we want to find this area under the graph from 1 to 5, right? So first of all, we take one trapezoid, means the approximation we'll get is 2.4, but the actual value of ln 5 is 1.60943 something. So it's bad. So let us try with two trapezoids. So we divided the interval into two subparts, 1 to 3 and 3 to 5, and we added the area of these two trapeziums. So we'll get 1.86. As you can see, first we got 2.4, now we got 1.86. We are getting closer and closer to the ln 5. As we increase the number of trapeziums, we can see we are getting closer to the solution. So n is equal to 6. The question we solved, we'll get 1.636436. We got 609. So for example, if we choose some 10 subintervals, we are dividing the interval into 10 subintervals and we got more accurate result. If you want even more accurate result, you can go until 20, 21 here. As you can see, the value is 1.61 and 609. So if we divide the interval into more and more subintervals, we'll get more accurate. If we divide the interval into 100 subintervals, we got accuracy up to 3 decimals. If you want even more accuracy, we can divide the interval into even more finer parts. That's the basic idea behind the trapezoidal rule. So, any questions? So yeah, please record your attendance again. Scan this QR. We'll open the form for 10 minutes. And in the meanwhile, if you have any doubts, you can ask in the chat. We'll try to answer those questions. So yeah, one of you has asked why we use specific quadrilaterals like rectangles and trapeziums in integration. So because they are more accurate. See, if think about it, I said right in the Simpson's rule, we use parabola to approximate, but for these are called first order methods. If we approximate the curve with a straight line, so basically we can't use squares because the function always won't be in such a way that squares are useful. So rectangles are like rectangles and trapeziums. They are most useful if we divide the subinterval into finer parts. So that's why trapezium, as if the bending of the trapezium is not too much slope, if the trapezium doesn't have too much slope, it's useful mostly to calculate the area under the curve. Yeah, we'll be closing this form in 3-4 minutes. Please fill out the attendance. Last 2 minutes, we are closing the form. I hope you filled your attendance, and let's go to third part of the lecture, differential equations, ordinary differential equations. Yeah, first of all, what are differential equations? Differential equations are the equations which relate different derivative of one of the functions to and known functions. For example, let us see in this case dy by dx is equal to e power x. Here y is the unknown function. So it relates derivative of an unknown function to some other known or unknown function. That's the basic idea behind differential equations. And you might think we can solve these differential equations by using some method like taking the dx to that side and integrating. Yeah, but most of the differential equations can be solved this way. Very tiny amount of differential equations can be solved using these methods. That's why most of them doesn't have a closed form expression. So that's why we use numerical methods. As we discussed, to solve the equations which are unsolvable. So you may think, what's the use of differential equations? Differential equations naturally come up everywhere, like when approximating population growth, or for example, when we have temperature as a function of time and we need to find the temperature after some T amount of time. There are problems in real life, and when we are using like when we are solving electric circuits and using heat transfer, differential equations come up there. So they are naturally most occurring equations. So that's the idea behind differential equations. So let us see how to solve this numerically. Let's classes of differential equations. Differential equations are broadly divided into two classes: ordinary differential equations (ODEs) and partial differential equations (PDEs). So an ODE, ordinary differential equation, involves derivatives with respect to only one variable and its exact differential. dy by dx is equal to x plus y. And partial differential equations. These contains differential with respect to one or more independent variable. For example, see here there is del u by del t. These are partial derivatives, as Karthik said before. Keeping the other terms constant, we differentiate with only respect to t. Del u by del t is equal to del square u by del x square. This is an example of partial differential equations. Now let us see how to solve ordinary differential equations. The methods we show, like Euler's method and RK2, RK4 method, they are useful for solving ordinary differential equations. So yeah, Euler's method. The basic idea behind Euler's method is slope. We use, you know that derivative of a function is slope of the tangent at that point, right? We use this idea to get the solution we want. What are the basic things required for Euler's method is we need to have an initial solution at one point. Like for example, at x is equal to 0, the value of y is equal to 1, and the derivative, and as differential equation, we know the value of function itself is the derivative of that unknown function. So we need to know a point on the graph, for example, 0, 1 or 1, 1. And we use that point to get to the solution we want. So the basic idea behind Euler's method is, let us see a function. So at x naught, the value, this is an unknown function, by the way, we don't know the function. That's why we use these numerical methods to solve. And the value of the function is y naught. And for example, we want to find the value of this function at some x. We don't know the value. Let's represent it y. So the basic idea behind Euler's method is, here we draw a tangent to this curve. Let us assume this is the tangent to this curve. And as we know, differential at this point is the slope of the tangent. You know, dy by dx is equal to f of x comma y. So the slope of this line is f of x comma y here itself. So this is delta x. As we know, as we can approximate delta y with slope into delta x, because slope is equal to tan theta. So delta y by delta x is equal to slope. So we know the slope at this point. So we try to approximate the value of the function at x using this slope and the distance between 2 points. That's why this is the formula for Euler's method. This is delta y, yn minus 1 minus yn. This is delta y is equal to h is the small step size we choose. Generally, we choose the step size to be small to get accurate results, because if small enough, a curve can be approximated by a straight line. Here again, we are approximating the curve with straight line, if you observe. That's why we choose h small enough so that it's a good approximation. And the slope is represented by dy by dx, as we know. And here f of x comma y is the known function. Here in the previous example, it is e power x, as we saw before. So we know the slope at xn comma yn. So basically use this formula to get the next iterations. So if you observe this graph, we started here. This is the x naught point, and we want to reach this x4 point. So here we found out the slope of the curve because we know x0, y0. And we took a small step. The step size is h. And we reached some x1. And from there, we again know the x1, y1. So we basically take another step and take another step. As we can see, it diverges from the original curve. But if we choose h to be small enough, this divergence can be neglected. So let us see an example to understand it better. Yeah, here dy by dx is equal to y in this case. And the initial point is 0, 1. At x is equal to 0, the value of the unknown function. Here y is the unknown function. We don't know what is y. And we take small step size, which is 0.1. So let us see. Y0 is equal to 1. So for example, if you want to reach y of some 0.3 or 0.4, that's the required solution. So y0 is equal to 1. Y1 is equal to initial y0, which is the value of y0 is 1, plus slope at this point. Here the slope at this point is given by y itself. The value of y is 1 at x0, y0. So 1 into step size 0.1 turns out to be 1.1. So this is y1. And y2 is y1, which is 1.1 plus again slope at 0.1 comma 1.1. This is the point we reached in the previous iteration, right? So at this point the slope is y itself, because as you can see dy by dx is equal to y. 1.1 into 0.1 step size. We are taking 0.1 step size every time. So we'll reach 1.21. So in the next iteration, we'll reach our required value 0.3. So as you can see, at x is equal to 0, we took one step and we reached the point 0.1 comma 1.1. After that, we took another step. Again, step size 0.1. We reached 0.2 comma 1.21. Again, we took another step 0.3 comma, and the point calculated is 1.331. So the exact solution of this differential equation is, if you know how to solve this, we'll take y this side and dx that side and integrate. And that's the idea, how to solve the differential equation exactly. So here the exact solution is y is equal to e power x, and e power 0.3 means y of 0.3 turns out to be 1.3499. While Euler method, it gives 1.331. So it is close enough. If we choose even smaller step size, we'll reach more accurate value. Let us see a table regarding this. Drawbacks of Euler's method. The main drawback of Euler method is the error keeps piling up. Here, as you can see, the error is some 0.01 when we reach 0.3, x is equal to. But if we want to reach e power 4, it takes 40 iterations, like with step size 0.1. But the error goes up to 9.34. Exact error goes up to 9.34. So to reduce this error, we need to choose smaller step size. See, if you observe this table, if we choose step size is equal to 1, so x is equal to 0, 1, 2, 3, 4. We took 4 steps, 4 number of iterations, but the result by Euler method is 16.00. But the exact value is near 54. The error, as you can see, the error is 38.6. If we choose smaller step size, the number of iterations increases, but the error gets decreasing. So as you decrease the step size, at the step size of 0.0125, the error becomes 1.34, which is good enough, but it takes 320 iterations. That's the main drawback of the Euler's method. See, as you can see, either Euler method is either inaccurate or slow. If we choose larger step size, it's inaccurate. If we choose smaller step size, it's slow. So it's computationally costly to perform more iterations. That's why we use other methods such as midpoint method and Runge-Kutta methods to approximate the solution for ODEs. That's the idea. That's the idea behind RK methods. Now I will show you a graphical demonstration of this Euler's method. Yeah, if you see this black graph is the graph e power x, and these red color dots are the points we reach using Euler's method with step size 0.1. So at first it starts out with the curve and it keeps diverging from the curve. If you increase the number of iterations, the error goes up to very high amount. So if we increase the step size, the divergence starts from the starting points itself. So for step size is equal to 1, we reach the point e power 4 in 4 steps, but the error is like 38. So that's why we'll reduce the step size to keep the error, to keep the divergence from the curve. But your Euler method is still one of the most basic method to solve the differential equations. So that's why we use other advanced methods such as RK methods or midpoint method to solve these solve these ordinary differential equations. Any questions? Yeah, so let's move on to RK methods. Now, Karthik will continue with the RK methods.
So now let us move on to some more accurate methods, the Runga-Kutta methods. Just as Satvik has mentioned, these Runga-Kutta methods improve the accuracy by a large extent without requiring the computation of higher order derivatives. Unlike the Euler method, which requires only one slope estimate for each step, these Runga-Kutta methods use multiple slope estimates for each step size. Some common RK methods include the second order Runga-Kutta method, the RK2 method, and the fourth order Runga-Kutta method, the RK4 method. Due to their accuracy, these are widely used in many kinds of engineering simulations. Now, why do we need these RK methods in the first place? As we have observed in the example, Euler method leads to significant errors as it uses only one slope estimate for each step. It does not account for the change of slope of the function along the step size. But these RK methods take multiple slope estimates into consideration, which account for the change of slope along the step size. Therefore, for a given step size, the RK methods improve accuracy by a large extent compared to the Euler method. So the second order RK method, the RK2 method, as the name itself suggests, uses two slope evaluations for each step. And the fourth order Runga-Kutta method, the RK4 method, uses four slope evaluations for each step size. Now let us study about the RK2 method. As the name itself suggests, this method uses two slope evaluations for each step size. There are a large number of variants for this RK2 method, out of which we will be considering one variant in which we compute the slope at the beginning point of the interval and at the ending point of the interval. The formula for this variant of second order Runge-Kutta method is given by yi plus 1 equals yi plus half times k1 plus k2 multiplied by h. Here h is the step size, k1 is the slope computed at the beginning point of the interval, and k2 is the slope of the function computed at the end point of the interval. So this is a graph which illustrates how the slopes are computed in the RK2 method. So this black dotted line represents the slope at the beginning point of the interval, which is k1, and this orange colored dotted line represents the slope computed at the end point of the interval, which is k2. We consider the average of these two slopes in our variant of RK2 method. Yeah. So this is how we compute the slopes k1 and k2. k1, which is the slope at the beginning point of the interval, is simply f of xi yi, and k2 is the slope f of xi plus 1 comma yi plus 1. As you can observe here, yi plus 1 here equals yi plus k1h, which is basically the Euler method used to compute yi plus 1. Therefore, we can say that this k2 is an improved estimate of the slope at the ending point of the interval, which uses the information from the slope k1. As I had mentioned earlier, this RK2 method has a large number of variants, out of which another common method is where we compute the slope at the beginning point of the interval and at the midpoint of the interval. Yeah. Depending on where we compute the slopes, the weights of k1 and k2 also vary. So you might get a question, how are these weights for k1 and k2 are determined? So the answer to this question lies in the Taylor series expansion. The RK2 formula is compared with the Taylor series expansion of the solution up to second order, and based on that some general conditions are derived for the coefficients of k1 and k2. Based on these general conditions and the variant that we choose for RK2, the coefficients of k1 and k2 are determined. Now that we have understood how this RK4 method works, let us quickly go through an example which will be taken up by Satvik.
Yeah, let's go through an example. So yeah, again we are going through the same example because at the end we compare all three methods. So basically, what's the idea behind RK2 method? We evaluate two slopes instead of one slope and average them to hope that it will improve our accuracy, right? So let's evaluate the first slope, K1. It is evaluated at the starting point itself. What's the starting point here? Again, 0, 1. So the slope at the starting point is dy by dx is equal to y. So the value of the slope is 1 itself. So K1 is equal to 1. So K2, we evaluate the slope at the end point we reach. As we can see in this previous graph, we evaluate the slope at this point. The next point we reach using Euler's method. So yeah, so first let us see which point we will reach. So with step size 0.1, the point we will reach is x 1 plus means y naught, which is 1 plus 1 into 0.1. This is the Euler's method, right? To reach the next point. This is equal to 1.1. So with the initial slope k1, we use the Euler's method and reached the point, this point. So we again evaluate the slope here. What's the slope at this point? The point we reached is 0, 0.1, 1.1, right? Here the slope is again y, so which is 1.1 itself. Keep in mind that we are not exactly going to this 0.1, 1.1. We are using that point to reach to the a better point. So let us approximate the slope now according to the formula. Y1 is equal to y naught, which is equal to 1 plus half times k1 plus k2. So this is the original point we are reaching in the graph. So y1 is equal to 1 plus half times 1 plus 1.1. So the point we will reach is times h, sorry, 0.1. So the point we will reach is 1.105. So x1 comma y1 is equal to 0.1 comma 1.105. In the Euler's method, if you remember, we reached the same point 0.1 comma 1.1, but here we are reaching 1.105. So this is a much more better approximation than the Euler's method. So we evaluated two slopes and averaged them to get to the better slope. And with that better slope, we took a full step size and reached the point 0.1 comma 1.05. As you can see the further calculation, in this case, as dy by dx is equal to yn plus 1 turns out to be 1.105 times yn. In this case, it turns out to be in such a way. So the next consecutive points are powers of 1.105. So first we reach 0.1 comma 1.105, and next we reach 0.2 comma 1.221 and 0.3 comma 1.3492. Here, if we see, we reached up to 3 decimals of accuracy. So it is better than Euler's method. So let's summarize RK2 method. So the RK2 method is first we will evaluate the slope at the starting point, and we will evaluate the slope at the ending point, which is reached by Euler's method, and we average both slopes and take a full step. So we reach a better point than the previous points. Now let's go through any questions before going to RK4. So yeah, one of you has asked how to decide the weights, right? So basically the weights come from the Taylor series. So there are many variations of this RK2 method. One of the variation involves we'll only reach half the step size and evaluate the slope there, and the weights would be 1 by 3 and 2 by 3 instead of half and half. So there are many variations. In the variation we are teaching you, it's just a starting point and end point. So average of both of them. So the weight would be equal, half and half. Yeah. So yeah, now Karthik will take on the RK4 method.
Now that we have understood how the second order RK method works, let us move on to a more accurate method, the fourth order Runge-Kutta method. As the name itself suggests, here we consider 4 slope estimates for each step size. This is highly accurate compared to the Euler method and RK4 method, which makes it one of the most commonly used RK methods for solving ordinary differential equations. Just like the second order RK method, this fourth order Runge-Kutta method also has a large number of variants, out of which we will be dealing with the most common variant in this session. Due to its popularity, this variation of RK4 is also known as the classical fourth order Runge-Kutta method. The formula for this classical RK4 method is given by yi plus 1 equals yi plus 1 by 6 multiplied by k1 plus 2k2 plus 2k3 plus k4 times h. Here k1, k2, k3 and k4 are the slopes that we compute in this RK4 method, and h is the step size. So this is a graphical illustration of how we compute the slopes in this particular variation of RK4 method. Here k1 is the slope computed at the beginning point of the interval. K2 is the slope computed at the midpoint of the interval using the information from K1. K3 is the slope again at the midpoint of the interval, which is computed from the information from K2. So K3 is just a better estimate of the slope at the midpoint of the interval, which builds upon the information from K2. And K4 is the slope computed at the ending point of the interval, which uses the information from the slope K3. So this is how we compute the slopes K1, K2, K3 and K4. So K1, the slope at the beginning point of the interval is simply f of xi yi. K2 is f of xi plus half h, comma yi plus half k1h, which is the slope at the midpoint of the interval building upon the information from K1. And K3 is a better estimate of the slope at the midpoint, which builds upon information from K2. So K3 is equal to f of xi plus half h, comma yi plus half k2h. And K4, the slope of the step and the slope at the end point of the step is simply f of xi plus h, comma yi plus k3 times h. So how are the weights of these slopes determined in RK4 method? Just like RK2 method, here also we compare the RK4 formula with the Taylor series of the original solution up to the fourth order, and we derive some general conditions for the coefficients of these slopes. Depending on the variation of the RK4 method that we use and the general conditions that we have, the weights of these K1, K2, K3 and K4 are determined. For example, for this variant of RK4 method, the classical RK4 method, the weights are 1, 2, 2 and 1 for the slopes K1, K2, K3 and K4 respectively. The accuracy of the RK4 method is greatly enhanced by the assignment of greater weights to the slopes at the midpoint, which are K2 and K3 respectively. Now let us quickly go through an example to understand how this RK4 method works and how the accuracy is highly enhanced by this RK4 method. This example will again be taken up by Satvik.
Yeah, let's go to the example of RK4 method. So yeah, again we are taking the same example. dy by dx is equal to y and y of 0 is equal to 1 with h is equal to 0.1. So the idea behind RK4 method is we evaluate 4 slopes, right? The first slope we evaluate at the starting point itself. So K1 is equal to the slope at the starting point, which is 0, 1 is y itself. So it's 1. And K2. So we took half a step size. So the step size is 0.1, right? We take half of the step size and we'll reach a point using Euler method. And there we try to evaluate the slope. So we use the using the previous slope K1, we reach y0, which is equal to 1 plus K1, 1 K1 times h by 2, because we are taking half a step. Keep in the mind, we are not reaching this point, we are just reaching it temporarily to evaluate the slope there, which gives 1.05. Yeah, 1.05. And using this slope, we again reach another point from the initial point itself. See, the initial point is 0, 1, right? We are reaching these points temporarily to evaluate the slope there to get to the final next point. So we reached this point once, and again we take half a step from the starting point to another point using the previous slope K2, which is y0 plus K2, which is 1.05 into 0.1 divided by 2. It turns out to be 1.0525, I guess. Yeah, 1.0525. And using this K3 improved slope, we finally take a entire step forward and reach a point K4. K4 is equal to 1 plus, which is y0 plus K3 means 1.0525 into h 0.1. Here, as we can see, we are using the entire step size. Here we used h by 2, but here we are taking a full step size. So it turns out to be 1.10525. So these are the 4 slope estimates. Using all these 4 slopes, we'll average them in such a way that with giving the weights 1, 2, 2, 1, we gave more weights to the midpoints because, as he said earlier, it makes more sense it is more accurate to give the more weights to the midpoint. So as we can see the calculation here, in this case, it turns out in such a way that K1 is always yi, means the y coordinate at the ith step, and K2 turns out to be 1 plus h by 2, and K3 turns out to be yi into 1 plus h by 2 plus h square by 4, and K4 turns out to be this value. And always it turns out in such a way that in this question, yn plus 1 is equal to, if you remember, this is the Taylor series for e power x, and up to the fourth degree, because we are using RK4. It is a fourth order method because it approximates the function until fourth order times yn. So here we reach this point. If you remember, in Euler method, we reached 1.1. In RK2 method, we reached 1.105. Here we are reaching 1.105170833. And so we are reaching this point finally. We reached 4 points temporarily and used the slopes there to get to this final point, 1.1571105717, like that. And after this, we reach 0.2, 1.2214, and 0.3, 1.3498. As you can see, again, the exact solution is e power x. E power 0.3 is 1.3498588. 1.3498584. So we got 6 decimals of accuracy. So as you can see, RK4 is more accurate as we do more slope evaluations. Let us compare these values. We used the same example everywhere to show you this comparison properly. At starting, the x coordinate is 0, and Euler method and every method initial guess is 1, 1, 1, 1. And exact solution is also e power 0 is 1 itself. So if you take one step size in Euler method, we reach 1.1. In RK2, we reach 1.105. In RK4, we reach 1.105171. It is accurate up to 6 decimals, as you can see. And in point 2, after we take another step, we reach 0.2, 1.21 in Euler, 1.22102, 1.221403. As you can see, RK4 is exactly matching up with exact e power x until 6 decimals. It diverges later, but until 6 decimals is good enough. And 0.3, 1.331, 1.349, 1.349 again. As we can see, RK4 is most accurate out of all these 3 methods. That's why RK4 is most used practically. So let us see a graph to visualize the RK4, RK2, and Euler's method. As we can see, this is the result for Euler's method, red color points. And these green color points indicate RK2 method, and these blue color points indicate RK4 method. Let's start with the initial points. Here the step size is 0.05. So let's make it 0.1 to visualize it more accurately. Yeah. As you can see, this red method means your Euler's method. It diverges from the original curve. Here, original curve, blue curve, and the green curve, RK2, RK4, are superimposed at the starting points. Means they are very much accurate for the starting point 1, point 2. But the Euler's method diverges from the starting itself. As you can see, the gap between the curves increases. Red one is the Euler's, and this blue green superimposed is RK2, RK4, and the original curve. As if we zoom more, we can see the blue color method, which is RK2 method, is also getting separated. But here the green color method, which is RK4, is very much close to the curve. It only starts diverging after we reach some points. So as we can see, Euler is least accurate, RK2 accuracy is moderate, but RK4 is the most accurate out of all of them. And finally, let us see some comparison between these three methods and practical applications. Karthik will take up on these. In the meanwhile, if you have any doubts, you can ask me. Let us pause for 1 minute.
Okay, so before we move on to this table summarizing all the three methods, let us answer a simple question. What to do when we can't isolate dy by dx into the form dy by dx equal to f of xy. In such a case, we can't apply the RK4 method. These RK methods are only limited to the equations of the form dy by dx is equal to f of xy. For equations of other kinds, we have some other methods which can be used to obtain an approximate numerical solution. Now let us move on to this table which summarizes all the three methods for solving the ordinary differential equations: the Euler method, the RK2 method, and the RK4 method. As we have discussed earlier, the Euler method approximates the Taylor series up to the first order, which means it matches the Taylor series expansion of the original solution up to the first order only. Similarly, this RK2 method matches the Taylor series expansion up to the second order, and this RK4 methods matches the Taylor series expansion of the original solution up to the fourth order only. Like we have discussed earlier, the Euler method requires one slope evaluation for each step, whereas the RK4 method requires 4 slope evaluations for each step. And as the number of slope evaluations for each step increases, the accuracy of the solution also increases. At the same time, the computational labor involved in computing the numerical solution for that step also increases. As you can see, as the RK4 has the highest number of slope evaluations for each step, the accuracy is also the highest, whereas the Euler method has the least accuracy. Likewise, the computational labor is also the least for Euler method, whereas it is the highest for RK4 methods. Depending on their accuracy and computational labor, each of these methods have their own set of applications. Wherever lower accuracy can be accepted, we use the Euler method, not just where lower accuracy is acceptable, but for some simple ODEs like dy by dx is equal to some constant, Euler method is sufficient to solve the equation. But wherever we require some high accuracy, like engineering simulations, RK4 method is more preferable. And the second order RK method and fourth order RK method are not the only Runge-Kutta methods. There also exists a third there also exists a third order RK method, which requires 3 slope evaluations for each step size. Just like RK2 and RK4, this method also has a large number of variants. And we also have some higher order RK methods like the fifth order RK method, which requires 5 slope evaluations for each step, the sixth order RK method, which requires 6 slope evaluations for each step, and the eighth order RK method, which requires 8 slope evaluations for each step. The accuracy is greatly enhanced by these higher order RK methods, but the improvement in accuracy is outweighed by the computational labor involved in these higher order RK methods. As you can observe, even though the accuracy is highly enhanced by this RK8 method, which uses 8 slope evaluations, the computational labor is very high compared to the RK4 method. So in most of the cases, RK4 method is the optimal method used for solving ordinary differential equations. Now that we have learned some of the techniques used to solve ordinary differential equations, let us look at some of the applications. These are used in the projectiles to analyze the motion of satellites, rockets, and so on. Suppose that we have a differential equation like dy by dt equals some function of velocity and time. These numerical methods can be used to find the position of the rocket or any projectile at different instants of time. Similarly, this can also be used to predict the trajectories of moving parts of machines like slider crank, 4-bar mechanism, and so on. Not just that, these are also used in various fields such as heat transfer and fluid mechanics. And these can also be used to analyze the growth of biological systems like Satvik has mentioned earlier. If we have the equation for the variation of population with time, that can be used to analyze the number of species at a particular instant of time. Not just these, there are a large number of applications for these methods. In short, wherever we have to solve an ordinary differential equation, these are some of the commonly used methods. Not just a single ordinary differential equations, these can also be used to solve a system of coupled ordinary differential equations as well, but we will not be dealing with those in this session. Any questions so far? Right. If there are no questions, let us summarize what we have learned today. First, we have learned what numerical methods are and why they are useful in today's world. Then we have studied the Newton-Raphson method, which is used for solving equations and systems of equations. After that, we have moved on to the trapezoidal rule, which is used for numerical integration. Later, we have even analyzed some common methods used for solving ordinary differential equations, namely the Euler method and the RK2 and RK4 methods. We have even compared these three methods in terms of their accuracy and computational labor. Not just that, we have even gone through some applications for each of these numerical methods. So that is all for this session. We will be giving you an assignment based on this topic, in which we will attach the links to these slides and the Desmos demonstrations which we have shown in this session. And we will also be recommending you a reference book for further information. That is all for today's session, people. Thank you and have a nice day, and keep enjoying math.